Okay, so this is a recording of section 10.4, the comparison tests. And so let me go ahead and share that screen. Okay, so the comparison test, there's actually two different comparison tests that we're going to go through in this section. There's the term comparison test and the limit comparison test. So the term comparison test is where we look at the term by terms. Okay, so it says let our series be a series with no negative terms. If the series converges, then there is a converging series where the terms a sub n are less than or equal to c sub n for all n. So in other words, if you compare term by term to a converging series, and each of your terms less than a converged series, then your series converges. Or if your a sub n, the series is going to diverge if there's a divergent series of non-negative terms where a sub n is greater than or equal to d sub n for all n. Okay, so there you compare term by term to a diverging series. So if your series term by term is greater than a diverging series, then it diverges. Or if it's less than a converging series, then it converges. Okay, now the things that are help us are if we know the geometric series, the P series, and the harmonic series. Those are known series that that converge or diverge in the sense of the P series, depending on what we know. What the P is, it'll converge or diverge. So if we have knowledge of those series, those are the series that we typically use to compare it with. Okay? So, for example, with the P series, all right, so we know that, if it's as an integral or as a series, 1 over x to the p, 1 over n to the p, it diverges if p is less than or equal to 1 and converges if p is greater than 1. So if we compare our series to a p series, depending on we choose if we want to compare it to a diverging series, then let p be less than or equal to 1. If we want to compare it to a converging series, then we choose p to be greater than 1. And so a P series is great to compare to because we know if it diverges or converges. Okay, so for example, here we know the harmonic series diverges. Okay. So the harmonic series, you start with n equal to 1. So 1 over 1 is 1. Then 1 over 2, 1 over 3, 1 over 4, 1 over 5, etc. So we know the harmonic series diverges. Geometric series is also one to compare to, good to compare to, because we know that a geometric series, if the absolute value of the r is less than 1, then the geometric series converges. So like here, where the 3 is, that's like your a sub 1. And then you have your exponent, here's your n. And then the r, the number that's being multiplied by each time in your geometric series, that's your r value. So if the absolute value of r is less than 1, that's a series that converges every time. So the more that you use these, the more you'll memorize. You'll know, oh, that's a converging geometric series, and oftentimes you can tell that just by looking at it. Okay, So first we have the comparison tests, or I've inserted the word term here because just to differentiate it from the limit comparison test. So I put in term here. Okay. Okay, so number one, a good series to compare it to is the harmonic series. So that's the sum as n goes from 1 to infinity of 1 over n, because 1 over n is known to diverge. So the harmonic series is a great one to compare it to. Okay, then you have these series. So I'm not sure why it's 1 over n to the p. So let's write it right there. Let's close that off. All right, so if p is less than or equal to 1, the series diverges. If p is greater than 1, the series converges. And then the third one, the geometric series. There, if the absolute value of r is less than 1, so this is another way to write it. -1 is less than r is less than 1, the series converges. So that's the same thing as the absolute value of r is less than 1. So you can write it either way. And then otherwise, the series diverges. So these are the great series to compare to, okay? So it says, let A sub n be a series with no negative terms. If there exists a converging series where each term is bigger than the A sub n terms, then the series converges. So this is the same as what we said before. It's just kind of written out a little bit easier for you to fill in the box. If there exists a diverging series for which each term is smaller than the A sub n terms, then the series diverges, okay? So if your series is bigger than a diverging series, it diverges. If it's smaller than a converging series, then it converges. Okay, so applying the term comparison test, okay? Oops. Okay, so let's say that we want to compare 5 over 5n minus 1. So just kind of think of the term. So if n is 1, then that would be 5 over, well, 5 minus 1 is 4, so 5/4. If n is 2, then we get 10 minus 1, so 5/9, 5/14, etc. Okay. All right. So now if you kind of think, well, do you think that that's going to converge or diverge? So let's say we think it's going to diverge. Then what we want to do is compare it to a diverging series like 1 over n. So see, 5/4 is bigger than 1. 5/9 is bigger than 1/2. 5/14 is bigger than 1/3 and 1. Okay, and so if each term is greater than the nth term of the diverging harmonic series, so therefore it diverges. Okay, so that's kind of the process there. If you think your series is going to be a diverging series, then compare it to a diverging series. Okay. All right, so practice 1. So here does the series 1 over n factorial, does this diverge or converge? Okay, so 1 over n factorial, that would be 1 over, and n is going to go from 0 to infinity. So 0 factorial, remember, is 1. So this would be 1 over 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. Okay, so go ahead and pause the recording and then see if you can work this out and figure out if it converges or diverges, and then we'll go over it. Okay, so kind of working these out, that's what I would do next, is to figure out exactly what numbers these are. So 1 factorial is 1, so 1 over 1 is 1. 2 factorial is 2, so you get 1 over 2. 3 factorial is 6, so 1 over 6, 1 over 24, etc. Okay? Now, if we compare this to a converging, let's see, this would be a geometric series. Okay, so we could write it like this. N goes from 0 to infinity of 1/2 to the n. So 1/2 to the n is going to be 1/2 to the n is be 1. 1/2. So 1/2 to the first is 1/2, and then 1/4, and so on. Okay. So what we have here. So okay. Well, actually, wait. What am I doing here? Okay. So if we have, okay, okay. So as we're comparing these, okay, see we have 1 is comparing to 1, and then 1 is comparing to 1 again, so it's equal. And so then we have 1/2 compares to 1/2, and then 1/6 is less than 1/4, etc. Okay. So let's write these up again. So this is like 1 plus 1 plus 1/2 plus 1/6. All right, and then this one is 1 plus 1 plus 1/2 plus 1/4. And you can go on. And so you can see for the first few here, they were equal. So they tied. And so it's kind of hard to tell until you go from the 4th term on, then the 1 over n factorial is in fact less than 1 over 2 to the n. So since 1 over 2 to the n is a converging geometric series, and the one that we're interested is less than that, then it converges. Now, if we want to know what the geometric series converges to, if we write that as 1 over 1 minus 1/2, so remember it's a sub 1, let's see, a sub 1 over, let's see, what's the formula? R minus, I forgot the I forgot the formula to write it. Let's see. The Well, it's in the notes, and when we talked about geometric series earlier. Um, but once we see that it's less than that, then we know that the series that we're interested in converges. Okay. So when you first you write out the terms, okay, and um, and then you start comparing term by term, okay, and then when you say, oh, it's less than this, then so if you compared it first to 1 over n, then what would happen is you would get less than a diverging series. So if you get less than a diverging series, you don't know if it converges or diverges. The way the term comparison works, if it's greater than a diverging series, diverges. If it's less than a converging series, it converges. But otherwise, you won't know. So 1 over n, comparing it to 1 over n, we don't get any answer here. But when we compared it to 1 over n squared, we could get that it's, let's see, it's let's see, we're n squared 1/4, 1/9. So this would be equal, greater. So then see, that's greater than a converging series. So neither one of these is going to work. So that's why we want to compare it to the geometric series. So that's really the trick in this section, is learning like which one to compare it to. And if you, frankly, if you try 2 or 3, then, and you can't get it to work, then I would move on to a different method. Okay. The idea is if you think right away, I'm going to compare this to the harmonic series, and oh, it's bigger than that, and boom, you're done. Okay. So if you can get the right one to compare to right away, then you're in luck. Oops. So, or you could compare to a P series, 1 over into the third, where because the P is greater than 1, it would converge. Okay, so you could try that one. Okay, so let's go on to the second part, the limit comparison test. So here, what you do is so you have these two series. A sub n is the series tested. B sub n is the series known. Okay, so you pick a series that you know, like the harmonic series or P series, geometric series again, that you know that it converges for sure, or that it diverges for sure. Says suppose that a sub n is greater than 0, so they got to be positive series. Okay, you what you do is you make a fraction. So again, the series tested goes on top, the series that you know goes on bottom. So if you take the limit, so that's why this one's called the limit comparison test. So when you take the limit, if you get a constant number, a positive number, then they either both converge or both diverge. And so that's great, because remember, you've picked a series that you know converges or diverges. Okay. So if you get a number, then you're done. You're going to know the answer. If you get 0, then if you've picked a converging series, then your series converges. But if you get 0 and your B sub n, you're the one that diverged, you don't know the answer. If you get infinity and B sub n, the series that you know diverges, then A sub n diverges. Okay. So if you get 0 and infinity, then sometimes you'll know the answer. But if your known series converges and you get infinity, you get nothing. Okay, you won't know anything. Okay, so let's kind of see how this works. It says use the limit comparison test to see if this converges or diverges. So we can write this out, 2n plus 1 over n plus 1 squared, which would be 2n plus 1 over n squared plus 2n plus 1. Okay, so then the question is you kind of, after you've done some of these, you start maybe getting a gut feeling over whether it converges or diverges. Okay, so then that is going to affect which one you select, which series you select to begin with, what you think it is. Now, if you're wrong, it doesn't, it's okay. I mean, you can, a lot of times you'll still be fine, but it can make it easier if you get right. Okay. So now with these, what I'm going to do is I'm going to compare this to the harmonic series 1 over n. Okay. Let's see. So I'm going to compare 2n plus 1 over n squared plus 2n plus 1 to 1 over n, which is a diverging harmonic series. So I know that diverges. Now, why did I pick that one? Well, I guess because I'm thinking, because the exponent is bigger in the denominator, then I'm thinking this whole thing is going to go like, say, constant over infinity. So that would maybe, I don't know. Uh, you're just kind of using your guess, your best guess. Okay. Now, when you take the limit, okay, so let's look at this. When I take the limit of, this is my original function over 1 over n, I'm going to rewrite it as um, multiply both numerator and denominator by n over 1. Because remember, dividing by 1 over n is the same as multiplying n over 1. And so then what I'm going to get, whoops. Okay, actually, okay, so when I multiply numerator and denominator by n, let's see, I'm going to get, so I'll get, where's that step at? 2n. Oh, so, okay, so I see what I did is I actually divided by the highest power in the denominator to simplify that complex fraction. And so then, so here, multiplying, I actually, multiplying by, dividing by 1 over n is the same as multiplying by n. So I could do it that way. Okay, so I'm kind of showing two ways that you can simplify this. Okay, or what I can do is if I divide everything here by n, by the highest power of n, then I'm going to get 2 over n plus 1 over n squared, and then n squared over n squared plus 2 over n plus 1 over n squared. And so when n goes to infinity, this will go to 0 plus 0 over 1. Whoops. So this will go to 0. Okay. So let's see, if I'm multiplying numerator and denominator by n, I get 2n squared plus n over n squared plus 2n plus 1. Okay, okay. Okay, let's, you know what, this part in green, I think. I'm just gonna get rid of that. Because that's just the original function here. I'm actually doing the in the limit comparison test. Let's go back to what I'm doing here. Okay. I think I got you a little confused with that green part here. Okay. So I'm taking this and comparing it to 1 over n. Okay. So here's my original function. Here's what I'm comparing it to. Okay. A known diverging series, harmonic series. Okay. Now, dividing by 1 over n is the same thing as multiplying by n over 1. And so then I get this limit. When I calculate this limit, I get 2. Okay. So I could do that by If you don't see that right away, you can work it through on L'Hopital's rule or whatever. Okay, but I'm going to get 2. So then what you do is say, all right, so I got 2. What does that mean? Well, that means, so I got a number. So I got a number constant, then the series both diverge or converge. Since I compared it to a diverging series, then my series diverges. So that's the answer, it diverges. Okay. Okay, now, before you do practice 2, okay, notice there's, depending on if you have the updated version practice 2, there was a little typo. And so, or make sure that you do it this way. It's 1 over 2 to the n, and then minus 1 is not part of the exponent. So it comes down. So make sure it's written correctly on your paper before you start this. So go ahead and pause the recording and then see if you can do this one. Okay, so let's try this one. So, okay, so this is one in the book, and they're kind of showing you, say, hey, we think this is going to look kind of like 1 over 2 to the n. So that would be a geometric series. So 1/2 to the n. So 1 to the n, 2 to the n. Okay. So then that would be the geometric series where r is 1/2. Okay, that is going to converge. Okay, because r is less than 1. So if we compare it to that, let's take the limit. Okay. Uh-oh. Okay, so let's try this again. It looks like my tablet here is frozen. Okay, there we go. So we're going to take the limit. So this is the series in question. So 1 over 2 to the n minus, and we're going to compare it to 1/2 to the n. And now you can put the 1/2 in parentheses if you want to. So when we take the so here, if we take the multiply, let's see, by top and bottom by 2 to the n to get rid of this, so it's not a complex fraction, then it actually becomes 2 to the n over 2 to the n minus 1. Now, when we take the derivative of 2 to the n, that's a little tricky. Okay, oops. Let's see, what am I doing here? Let's get rid of that. Okay, so 2 to the n, I'm just doing another example over here. So 2 to the n is a little tricky because when we use L'Hopital here, the derivative is 2 to the n times the natural log of 2 times the derivative of n, which is 1. And then the derivative of 2 to the n minus 1 is going to be the same thing. And so then when we cancel, we just end up with 1. Okay. So remember, we compared it to a converging geometric series. So when we're when we get a constant like 1, then the series either both diverge or converge. So since we compared it to a converging series, our answer is it converges. Okay. Now, let's see. So what am I doing over here? Okay, so I kind of did it. I compared it to 1 over x squared, which is another converging series. And so then when I compared it there that way, I simplified the algebra, and then I also ended up with a constant. And so then you get it that way too. Okay. So there's nothing to say that you couldn't do it a different way. Let's, but I don't want to cover that up because it. So this is probably the easiest way if you remember how to do the derivative of 2 to the n. Okay. So let's see. So then what if we compared it to 1 over n? If we compared it to 1 over n, so then we'd multiply top bottom by n of 1. So we'd get n over 2 to the n minus 1. So then when we plugged in, we'd get infinity over infinity. So then we'd want to use L'Hopital's rule. And so then we get 1 over 2 to the n times the natural log of 2 times 1. So as n approaches infinity, we'd get a constant over infinity, which would be 0. So then we would get nothing from that. So remember, if we get nothing, if we get 0, and we're comparing it to a diverging series, okay, so because we know the series diverges. So it just depends on what you compare it to. So in this one, if we ended up with 0, then we got and we started with a diverging series, then that's no good. Okay. So it really matters as far as what series you're comparing it to. Okay. So the last little part of this is actually also on the beginning of the next video, I think, but let's just go through it anyway. So the natural log of n grows more slowly than n to the c. So I don't, again, this should be over here. For any positive constant c. So natural log of n grows more slowly than n to the c. So when we're talking about comparison, so we want to know, okay, does this series converge or does it diverge or whatever? Okay. So here, when we're kind of thinking more about the term by term comparison. So you say, well, the natural log of n over n to the 3 halves is going to grow more slowly than n to the 1/2 over n to the 3 halves. Okay, so these are the same. I'm using the same function here. Okay, but see, what the reason why I'm picking this is we're saying that it grows, the natural log of n grows more slowly than n raised to any power. Okay, so I'm using this n to the 3 halves so it'll match the denominator here. Okay, n to the 1/4. Well, there's nothing really special about that, but let's just see what happens here. Okay, so as I is I'm simplifying into the 1/2 minus 3 into the 4th minus a negative 3/2. Oh, bringing it in the denominator. So then I have 3/2 minus 1/4. So that becomes 5/4. So all the reason why I picked into the 1/4, I really could have picked anything. It would have ended up giving me a number that's bigger than 1. So that means it's a converging p-series. So that means it converges. Okay, so let's see if that makes any sense at all. Here, let's try the practice problem. Okay, so you can do it using any limit comparison, term comparison, whatever. So go ahead and stop the recording and see if you can figure this one out. All right. So we're going to compare it to a converging p-series, 1 over n squared. Why did I pick that one? Well, because I have an n squared in here. I have some other junk, but I'm going to compare it to 1 over n squared, and so you want to pick one that you know converges or diverges. So this is a converging p-series where p is greater than 1. It's 2. So 1 over n squared, that's a converging p-series. So now I'm going to compare. This is my original for comparison. Okay, 1 over n squared, that's what I'm comparing it to. Okay, so now what I'm going to do is, again, dividing by 1 over n squared is the same as multiplying by n squared. So when I simplify, I get n squared plus n squared natural log of n over n squared plus 5. So when I plug in infinity, I'm going to get infinity over infinity. So we're going to use L'Hopital. So I get the derivative of n squared is 2n. The derivative of n squared natural log of n. There it looks like I've got to use the product rule. So the derivative of n squared is 2n natural log of n plus n squared times the derivative of natural log of n is 1 over n. And then the derivative of the denominator is 2. All right, so let's see. All right, so then if I simplify this, n squared times 1 over n is just n. So n plus 2n is 3n plus 2n natural log of n over 2. So it looks like then I would get infinity over infinity. So I do L'Hopital again. So I get 3 plus, so the derivative of 2n is 2 times natural log of n plus 2n times 1 over n over 2. Okay, so that one's going to give me, let's see, the n's cancel here, so I get 2 plus 3 is 5, plus 2 natural log of n over 2. So that's just infinity. Okay, so not infinity over infinity. That's just going to give me infinity. Okay. All right, can I get that up here? Yeah. So that tells me nothing. Why? Because I started with Converge series. So if I get infinity from a converging series, then that's no good. That tells me nothing. So what I'm going to do here is now let's try the term comparison. So all right. So what I did is I wrote down the first few terms, okay, of my original series. So I did 1, 2, 3, 4, and so I got these fractions right here. Okay, so if I compared it to 1 over n, well, let's see, it starts off less, 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 less. So it, remember, if you compare it to a diverging series, you want it to be bigger. So that tells me nothing. So now if I compare it to a converging series, okay, and here's 1 over n squared, 1, 1/4, 1/9, 1/16. Okay, so my series is, it's less, less, but then the third one, so let's see, 0.1499, 1/9 is 0.1111. Let's see, that one is gonna, that doesn't help either because it doesn't stay less than. Okay, so then you got to come up with something else. All right. Okay, let's see. Wait. Oh, this is the same thing. So what does that mean? Okay. So what that means is that for right now, I mean, that we are not going to be able, we don't know. We tried everything this section. We tried limit comparison. We tried comparing it to a converging series. We tried comparing it to a diverging series. So it might be that if we picked another series, we might be able to come up with the answer. But what I'm really trying to get you to see from this example is that that we need other tests. We need other things that we can do. And so it might be one that we already learned. It might be one that we're going to learn in the next section or whatever. But that these tests do have limits. They're not, no pun intended, they have limitations on what they're able to tell us. Okay. So so in some ways, I like the comparison tests because you either know the answer or you don't pretty quickly. They don't typically take. There was a one that we had to do L'Hopital several times, but typically they don't take too long, but they're foolproof. That there's going to be ones that don't that aren't answered it. So what you want to do is you go through and you continue to learn more of these tests. They're like tools in your toolbox. And if you get really good at one, you might be able to do 80% of the problems using that one test. But there's always going to be something where you're going to want to learn a different test. So, okay. All right. Well, I'm going to go ahead and stop this one and for 10.4 and stop the recording. And good luck to you.